welcome to week 6. Everything is getting better and better all the time. I've been looking over student work, student labs, talking to everyone's tutors, and I'm feeling very happy. I was a bit nervous at the start of the course because it seemed that a lot of people were taking a while to get started, or maybe you were starting already behind or something, or there were just some problems. But it seems now at least half the tutes are rocketing forward and people are completing the labs and everything's being done. So well done, everyone. That's fantastic news. Now this week, to give you all a chance to get your hands dirty with coding, because I still have this niggling concern about everyone not doing enough coding. We've done a lot of the course already and there's not much coding going on, and when it happens, some people are still having a few problems. So the tutors and I had a meeting and we decided really I could talk until I'm blue in the face, but the best way to learn coding is to do it. So we have this week something we call the Spring Festival of Coding Week Lab, which is a very exciting thing. So if you've seen the lab for this week, there are 4 questions in it. We've actually delayed the release of task 2 to give you time to work on this lab. We didn't want task 2 coming out while you're stuck on this lab. So there are 4 questions, and you have, I think, till next, you even have longer than normal to do them. I think it's next Tuesday or possibly even later to do them all. You don't have to do them all. We only expect you to try them all, but we only expect you to do 3 of them. And if you look at the marking goes, there's a 1/4 of a mark if you do 1 of them, there's 1 mark if you do 2 of them, and there's 4 marks if you do 3 of them. And if you do 4 of them, there's 4 marks, and we'll ring a bell. So please everyone jump in and try and code these. We've picked the 4 examples very carefully. They're things you need to know for the course and that solidify the things we've been doing over every week in the course so far. So please throw yourself into that enthusiastically and make sure you get, only need to get 3 of them, but I'd try for 4 because that bell is pretty damn awesome. Actually, I did get a bell once. When we closed our stores department and we were saying goodbye to all the boys from stores, and it was a very sad day, I started avariciously looking at the front of the store's counter because it had a bell on it. And I said, it's really sad you guys are going, but can I have some of your stuff when you've gone? And they said, what do you want? And I said, I want the bell. So I've got one of those little bells, you go ding. And I always thought it would be good to put it in the lecture. Just put it up the front. And then if someone had a question, don't put up your hand. You just do what you're supposed to do when there's a counter. You come down and you just ding, ring the bell. So I'll bring it to the lecture one day. Maybe we'll even ring that. And I'll be on the phone and I'll say, hang on a sec. No, hang on. And you'll just ding. And I'll say, I'll be with you in a minute. No, hi, Mum. No. That'll be fantastic. Okay, so we even have a bell ready now, I realise. Today's lecture. The lecture note, the raw notes today are thanks to Wednesday 18 Oboe, Liam and Bernard's tute. So everyone give them a hand because I know they're going to take excellent notes today. Thank you very much. That's fantastic. Okay, now here's a beautiful modernist poem. You don't have to memorise it, of course, because you can put it in the textbook. It's very, very beautiful. It's bound to be in the test. It's very, very beautiful. Okay, so today we're talking about searching. And I thought, let's just revisit the whole searching thing, just look at the big picture before we dive into more details. Let's look at some of the things that might pop up when you're trying to do a search. So the first of all is, there are different sorts of searches. There's lots of different times you'll be searching and lots of different objectives you'll have. Let's just sort of tease out the idea of all the possibilities of searching. One is, do you know when to quit? Sometimes when you're searching, you know when to quit, and sometimes you don't. Here are some examples. Here are some example searches. Finding the solution to a maze. So there's many, many possible paths and journeys you could take inside a maze, and at least one of them will take you out of the maze. If you're searching for a solution to the maze, do you know when to quit? When? As soon as you get out. So that's a convenient property to have. It's very nice if you know when a search is going to quit. What if I asked you to find every solution to the maze? Do you know when to quit then? No, you've actually got to try every single possible way. Well, actually, maybe halfway through your search you can start to realise, like for example, maybe you can sort of build up some partial information. I guess maybe the maze looks like this. It's got an indoor, I'm just meaning a two-dimensional maze, say. And some stuff happens in an outdoor. And you've found all these paths, you found one path that goes like this or something. I'm not drawing all the walls necessarily. But you also noticed, maybe you noticed something like that. And maybe I've asked you to find the shortest path. I'm not asking you to find all the paths, I'm asking you to find the shortest path. You've found, and you happen to have, in your journeys, walked all around this wall to there and got out, and you've managed to walk all the way around this wall to there and got out. Oh, actually, let's make it more challenging. Maybe the gap's down this end here. If you're looking for the shortest path, you might work out that you never need to enter this block. Does that make sense? Because it can't possibly be shorter than just skirting around the edges of it because you've walked all around the edge and they're sealed. So whatever you do inside there, you're going to have to come back out again. So if I'm asking you to find all paths, I guess you have to go through there because one journey is a ridiculous one that involves lots of dead ends and comes back through there. But if I'm asking you to find the shortest path, although you might not automatically know when to quit, you might be able to prune off sections of the search. And there might be certain paths you don't have to consider. So you don't have to look in every possible place for the thing you're looking for. You can start to trim it down a little bit. But you've got to be careful when you do trimming like that. I called that optimizing on Friday. You've got to be very careful. You could, for example, my daughter's doing mazes at the moment. She's 4. She never really likes doing something that looks like she's going backwards. So if she was all the way up here, okay, I'm just removing all the walls, just have to imagine there's lots of a maze of walls in there. She's all the way up there and she gets a choice between going that way and going that way. Or maybe it's even worse, maybe it's a choice between going that way and that way. She hates going this way. She massively prefers going that way. Even though you know a good maze designer will probably make you do things that look like backtracks in order to get out. But she hates doing that. So if we were to ask her when she can prune off sections of the search, areas she doesn't have to look at, paths she doesn't have to consider, she might say, I don't think you need to go down here. She might even say it more confidently. She might even say, you don't have to go down here, but that wouldn't be based on any proof like that enclosed region was. That's just based on some gut feeling she has. So you yourselves have to make sure when you're doing a search, if you're about to lop off parts of the search, that you're not doing it because of some gut feeling that you reckon that's the right thing to do, but that you actually have a proof that that's the right thing to do. Does that make sense? Okay, so let's return to our problem. Finding solutions to a maze. What about finding a library book given a serial number? Do you know how to terminate that search? Do you know when to stop looking?
When you've found it or you've checked all the books and it's not there.
Yeah, so if you find it, you can give up. If you don't find it, you have to actually search every single place in the library because someone might have put it back in the wrong spot. So you have to check them all. Good, well done. So sometimes you can give up. You can give up with a success. What about if you had to find a correct sorting network for 4 inputs? So I'm saying, how many sorting networks are there with 4 inputs? There's an infinite number of them. Remember, a sorting network looks like 4 lines with little links between them? How many correct sorting networks with 4 lines and any number of links in any position? Well, there's clearly an infinite number of them. But do you know when to give up if I'm asking you for a sorting network that correctly sorts? I'm saying, can you find one? It's clearly a search problem. You have to search all sorting networks. But do you know when to stop? When you find one? Yeah. What if I said, find the best sorting network for 4 inputs? Do you know when to stop then? No. It's harder, isn't it? What if you found one that could sort 4 inputs using 6 comparisons? Do you have to keep going? Yeah. What if you found one that sorted 4 inputs with, what did I say last? 6? 5 comparisons. You have to keep going? You have to keep looking? It's such an easy question. It's when I'm asking these easy questions, everyone's going, that's so obvious, I'm not going to answer. Because this was a tute question a couple of weeks ago, so I know you're all going, God, Richard, you're just asking us something that was in a tute. Okay, so basically, as you know from that tute a couple of weeks ago, using Shannon's limit, the smallest number of comparisons we have to do to sort 4 things is 5. Yes? Because 2 to the 5 is the smallest power of 2 that's larger than 4 factorial, which is the number of ways of arranging 4 things. So if you got to 4, yes, you could cut it off early. You could give up. And similarly, if you'd already found a network which was a solution with 6, you don't have to scan any networks now that have more than 6. Because if I'm asking you for the shortest one, then you're getting a bit of information. You've already found one that's 6 long, so as soon as you're building a network, once you've added 6 to it, if it's still not sorting, there's no point in adding more nodes to it, because it won't be the shortest. So you have some information about when you can give up, and that makes it convenient. But if you have no information about when to give up, if I said find all sorting networks for 4 inputs, well, you can never give up. You just have to keep going forever, unfortunately, because there's an infinite number of them. So be very careful when someone's asking you a question if you can give up or not. Now, all searches, in a sense, are a serial journey. If I'm looking for something, suppose I've lost my keys at home, which happens quite a lot. In looking for them, if you were to plot it from above, maybe take a film of it and look down, I'd be going from point A to point A to B to C to D, and I'd be looking at all these different spots. And you could plot that over time, and I wouldn't necessarily start at the front of the house and systematically zigzag backwards and forth, slowly scanning through the house like some sort of CAT scan or something like that. I'd probably go to the places I think it's most likely to be, and the places I can vaguely remember leaving it, and places I've lost it before, and then places that occur to me next. And I'd follow some random order, but no matter what I do, I'm necessarily engaged in some sort of serial journey. I'm visiting the places it might be once. And in fact, no, because I'm a bit hopeless in looking for things, I often visit the same place several times. But that's obviously an inefficient search. But I mean, your search algorithm could do that too. So all searching is really a serial journey. The different search strategies we look at and the different data structures for representing and supporting searches allow us to have different journeys and visit things in different orders. But notice, if we're doing a search that we don't know when to stop, so we actually have to visit every single spot, it doesn't really matter what order we visit them in. We've got to visit them all. So some of the data structures, which are really convenient for finding things early on, but they have a bit of extra overhead, maybe they require a bit more calculation, they're not actually so useful in those sorts of searches. Because in those sorts of searches, it doesn't matter if you find the best one early on, you don't know it's the best, so you can't give up, you have to keep looking. So you have to be very clear in your mind, I guess. Have I got the sort of search where I'm likely to be able to give up, and what sort of extra information have I got, before you start working out what search strategy am I going to use? Because ultimately all your search strategy is going to do, if it's a proper one, is systematically visit every node that you have to visit, and all the different strategies you're going to do differently is visit them in different orders. And I say node, but I mean possible solution. I said node because I was thinking of a tree. Remember last week we looked at searching on depth-first search on a tree and searching breadth-first search on a tree? And everyone was saying some were better than the others and others were better than some. But notice, if you've got to visit the whole tree, it doesn't matter at all if you do a depth-first search or a breadth-first search. You've got to visit the whole tree. So which one would you use if you've got to visit the whole tree? Well, it doesn't matter in terms of you've got to visit them all. So other criteria come into play, like which is the easiest to code? Which am I more likely to get right? Which one runs the fastest? Which one uses the least memory? And the answer to all of those questions is probably depth-first search. So you'd probably use a depth-first search. But if you had a search where you could give up early, as soon as you find it, you can stop looking, then then the choice between depth-first and breadth-first becomes a real important choice. Because if it's likely to be found earlier using a breadth-first, use a breadth-first. And if it's likely to be found earlier using a depth-first, use a depth-first. Okay, sometimes you have a search where you're not looking for the answer, the one, you're just looking for something that's near enough. Near enough's good enough. So find me the best way you can of packing items onto the shelves in the shop so we have the most generic brand products on display or something. And there's a million ways of, if you're at Woolies or some supermarket, there's a million ways of placing things on the shelf. There's too many things and too many shelves. The sheer number of combinations is just astronomical. It's so big that it's beyond a brute force search ever. You couldn't sequentially search through all the combinations. So there you just got to come up with something that's reasonably good. And to make your boss happy, maybe something that's better than the current way of doing it. So that's a near enough is good enough sort of search. We call that a heuristic search. And heuristic searches are sometimes exactly what you want. But notice for our next assignment, we're not asking for a heuristic search. We're asking for an actual correct search. Other interesting aspects to think about in searches are often once you've set a structure up that you're going to search, you do more than one search on it. You might search it many times. Like maybe you set up a dictionary. Maybe you're a word processor. You set up a dictionary with correctly spelt words, and every time the user types a word, you scan through the dictionary to see if the word's in there or not. And if it's not, you draw a little squiggly red line underneath it. So you'll be searching in that dictionary, if they're writing a 10,000 word essay, you'll be searching in that dictionary at least 10,000 times, probably many, many more. So it would be silly to design your search algorithm and data structure to support speeding up a single search. Rather than you should think of the problem holistically and think, what's the fastest overall way of doing this thing? So I know I have a large sequence of searches. Maybe I should set the data structure up so it optimizes efficiency over the whole sequence. So for example, and I'm thinking about word processors, they've probably got both criteria, don't they? No one wants to sit there waiting half an hour for the first word you type to be spell checked, just so all the remaining words will be spell checked really quickly. You actually have a demand that you want the first word to be spell checked reasonably quickly. But it would be nice if if you could use speed ups over time, so you use less of the process power for future searches. Does that make sense? But you still want the first one to be quite good. So, for example, we looked at self-adjusting sequential search. The idea of a search that updated itself and put more likely to be looked for words up front. That's an idea of, that's something that costs a bit of work each time, flipping the elements like that, but over the long sequence of searches, that will give us a better overall performance. So that's another aspect to think. Not just what are the operations I'm going to have to do, what are the searches I'm going to have to do, but what's the whole sequence of them I'm likely to get? And which ones occur the most often? Like, for example, if lookups occur very often, but adding things to your data structure occurs really infrequently, then it's probably worth, when you add something, doing a whole lot of extra work to put it in a clever spot to speed up looking up, rather than trying to speed up the adding operation, which you don't do very often. So you can speed it up by just dropping it at the front. Maybe it's actually worth scanning through the list and putting it in the right spot, or scanning through the tree and putting it in the right spot. Even though that gives you more cost for the add operation, it gives you less cost for the lookup operation, and if we've got many, many lookups to hardly many adds, then yeah. Okay, so look at the pattern and the relative frequency of all the operations you've got to do and think about the whole thing holistically. Don't be tricked into just thinking about the things individually. Also, sometimes your lookups are based on a set, and sometimes your lookups are based on a dictionary. So a set is just a collection of stuff. And something's either in the set or it's not. So I could ask you, tell me a word. Any word? Book. And I'll look and see, is it in the most 100 most commonly used words in English? I just have to look that up. And if you manage to say a word that's in the most 100 commonly used words in English, I'll give you a prize. And book, no, it wasn't. Sorry. But you nearly got a prize. So, do you want to try again? Yes, you get a prize. Okay, woohoo. There you go. Come and collect it afterwards. Would you mind giving him the prizes that I gave you before? Yeah. So, that's a set. A set, you're either in it or you're not, and there's nothing else to it. And the operation you ask is this an element of the set? And order doesn't matter in the set. I'm not asking, is that the most important word or the second most important words? I just need to know, is it in it or is it not in it? But the other sort of search you might want to do is a dictionary style search, where you're searching for a key, and you don't just want to know if the thing's in it or not, you actually want to return some extra data. Like maybe I've given you the barcode and you've got to give me the object off the shelf. Or I've given you the word and you've got to tell me how many times you've seen it. Or I'm giving you a student ID and you've got to give me someone's marks or something like that. So that's a dictionary style lookup. So again, different strategies are good for sets and different are good for dictionaries. As we'll see, I just want you to sort of think about the big picture before we jump in and do it. And the last thing I wanted to say was, this was a thought that I had on the weekend while I was watching my daughter play soccer, which is, do notice that the only way of finding something is looking for it. And I'm sort of here thinking of your programming and things like that, but just about uni and study in general. If you just sit there wistfully planning how you're going to look for it, but you never actually look for it, you'll never find it. You've actually got to sort of start looking. And I realised this when my daughter was playing soccer, and she just was looking at the ball and doing all this planning, but she never actually kicked the ball in more or less the whole game. And I'm watching her, and I'm just watching her and thinking, well, she's thinking a lot, but it's not helping the team. Because at the end of the day, if she doesn't interact with the ball, I guess she could spook out the other side and things, but basically interacting with the ball is all it's down to when they're that age. So I started shouting, and the other parents are shouting out wise advice like, mark number 8, and move together and compact and look out for the offside winger. And I'm just shouting, kick the ball! Kick the ball! So that's my general advice to solving problems in this course and things. Don't agonise and think forever about it because there's no point unless you actually start looking, you won't actually find it. Sure, maybe once you start looking you'll think of better ways of looking, and that's great, but don't spend your whole life just planning how you're going to look and not actually ever look. Okay, so we've got sequential searching. We looked at, the point of today's lecture is we're going to build up to a new data structure, a new way of supporting a search. So we're going to look at the way we have already done searches, and we're going to think what they're good for and what they're not good for, and hopefully that's going to indicate a problem that we'll then solve with this new data structure. So we've got sequential searches. That's when you just go through things systematically. You're not going to visit the same place many times like I do with my keys. So you go through things systematically, but just try them one at a time until you find it. And really the only optimization we had for that was maybe rearrange things so that what you're looking for is more likely to be at this end. Again, only useful if you've got the sort of search when you know you can give up. No point if it's near this end and you find it, but you can't be 100% sure you found it, so you have to keep looking. So if you've got to give up early search, then rearranging things to put the likely solutions near the front is a really good idea. Notice sequential searches are really good if you've got a sequential series of lookups. Like suppose I just had to go through all the books in the collection one at a time and do something to every single book. Then there's no advantage in using any fancy elaborate data structure. I might as well have them in the list and just deal with them in the order that I find them. Make sure the order I look at them is the order that they're in the list. But if I can somehow predict what order I'll be getting them, like maybe I sort them in alphabetical order and then I just make sure my program to update all the book records searches the books in alphabetical order, then if I've got a list of books in alphabetical order or an array of books in alphabetical order, I can process it as fast as can be. There's no disadvantage in using a list or an array. We often make fun of lists because they seem slow, but they're only slow if the thing you want is always at the other end. If the thing you want is always at the front, well, that's great. You can't get a better data structure than that. Absolutely perfect. Lovely. So if you've got a series of sequential accesses, sequential search can be good. If you need to know more than just the key, like for example, suppose it's important that I know the order in which the objects were added. Somehow that's important. Then a sequential, using some sort of sequential data structure or serial data structure makes sense because I can actually store them in the order they were entered. That's extra information, extra to the key. But like for example, I'm thinking of a stable sort. With a stable sort, you want it to sort the things, sure, but in case of a tie, so where the key can't arbitrate about the order, you want the order to reflect the order in which the things were initially entered. So for things like that, lists have great properties because they store this information in the serial nature of the list. So that's another time a sequential search can be actually a sensible data structure to use. A priority queue. A priority queue is an interesting sort of queue. It's actually, you know, like the traditional polite way of doing things. Let's look at the traditional polite way versus the oldie way of doing things. At the traditional polite way is you all push your shopping trolleys up and the first one that gets there gets served first and the last one that gets there gets served last. That's a queue. At oldie, what happens to me every time I go there is I push my trolley into the queue and a million people line up behind me and then the lady in front of me suddenly turns into a statue for some reason that no one can understand. And then suddenly a voice next to me says, "This checkout's opening now." And everyone peels off to join that checkout. But I can't go back because there's a trolley behind me. So even though I was there first, who gets to that checkout first? The last person in the line. It's a stack. They're just doing a stack all the time. So that's completely not right. Well, airports used to have the queue system. So the first person to turn up with their ticket was the first person that got served by the baggage check-in person. But now, what do they have? First class. Yeah, they have a sucked-in queue if you bought a cheap ticket. And we love you queue if you bought a ridiculously expensive ticket because you've got more sense and brains. So in those cases, as soon as any rich dude turns up, he gets right to the front of the line, essentially. Very unfair. In fact, I once was on a plane flying into somewhere and the plane was held up and I had to catch another plane that was flying out straight away, and this plane was landing and I had like a 2-hour window and I was nearly going to make it, and then the plane got held up and I said to the hostess, I'm really worried when this plane lands I've got to run all the way across Charles de Gaulle or some crazy airport, and I think I then had to jump on a bus which took me to a ferry which took me across the English Channel. There was this long chain of things, and unless I got off the plane straight away, and she said, no worries, I'll put you at the front. You can be the first one off when the plane lands. And then the plane's coming to land and this big fat businessman stands up in first class and he starts staring at me and I'm smiling at him and he's getting really angry and what's he angry about? And then he started saying, you're going to get off before me. And I said, yeah, I've got to catch this bus and a plane and a canal and a thing. And he said, oh, that's not right. I paid more for my ticket than you. I'm more important than you. And I said, and I just started laughing. It just seemed so ridiculous. And I just kept giggling to myself the whole way until we landed, and I left the airport giggling, running in front of him. But nonetheless, that's a priority queue. If that airplane had actually been having a priority queue, they'd have gone in front. So a priority queue is a data structure where things join the queue, sure, in any order, but the first one out of the queue is the most important one, the fattest one. So, when's a priority queue useful? Well, it's very useful sometimes if the idea being of a priority queue, the thing you're most likely to be searching for is sort of up the front of the queue, moves it right up to the end. So if you're doing, say, for example, a selection sort, where you've got to select the biggest one each time and put it in the right spot, then you select the next biggest and put it in the right spot and the next biggest. One way of implementing a selection sort is with a priority queue. You get your original items and you stick them one at a time into a priority queue. And the priority queue just has a rule that the most important thing is the biggest number or the smallest number. Then naturally, as you insert them, they trickle into the right position and you pull out the right position. Now, notice with a priority queue, if your lookups happen heaps more often than your inserts, a priority queue is a very sensible structure to have because it only has a big cost on your insert. I sort of said this already in the intro, didn't I? But your lookup speed is massively reduced if you're scanning through the thing quickly looking for stuff. And the last thing I wanted to say was looking for four-leaf clovers. If you were looking for a four-leaf clover, say you were just lying out in the paddock, if this uni had grass, and you were looking down to find a four-leaf clover, what would be the optimum strategy to use? What's the search strategy for four-leaf clovers? Radiation. Create new ones. I like the way you're thinking. Yeah, that's one way of sorting a list that I'd never thought of before. Take the items from the list, ignore their value, and rewrite new values in that are sorted. That's awesomely clever. Now, who when they were writing unit tests for a sort function would have thought to check? I bet you'd have all just written something to make sure that the output is in sorted order. Who would have thought to actually put something to make sure that the person hadn't cheated and changed all the values? That's another test that we've just realised we're going to have. Okay, so if you're searching for a four-leaf clover, do we have this property that, is it going to be a sequential search, is what I'm trying to ask. It probably is, in the sense that you have no real clue about where it's likely to be, and no spot is sort of any more likely than any other spot, and as you do each probe, and you find, no, that's a three-leaf, no, that's a three-leaf, no, that's a three-leaf, it's not really giving you any information that's going to help you tune your future probes to make them more efficient. So maybe the trick with looking for a four-leaf clover is to be systematic, is to grid the area out, make sure you don't look at the same clover twice, in other words, grid it out in some way and just systematically go through one at a time. And in fact, I was once at Macquarie University, which is a really lovely uni, which has some grass, and I was lying on it in a, we have grass, I know, I've seen some. Where is it again?
The huge oval thing at the front.
The huge oval thing at the front? Is that grass? No. Okay. Yeah, we have more than UT. Oh, now we're getting competitive. Okay. All unis are great. All unis are great, despite how much grass they have. And I was looking there, and I remember I looked down and I thought, oh, I could be working on this complicated statistical problem I've got to solve, or I could look for a four-leaf clover. I know, I'll look for a four-leaf clover. So I just started looking through a big patch of clover, and you know what? Because I was kicking the ball, what happened? I found one. And I thought, oh, I found a four-leaf clover. I'd never found one before in my life. I was a uni student. I'm going, I found a four-leaf clover. Wow, that's fantastic. I was so excited. And then I thought, well, maybe the key distribution isn't completely independent. So I started searching near it to see if its neighbours, parents, offsprings, cousins, maybe they're mutated as well. And sure enough, I found a couple of other four-leaf clovers near it. And I'm getting very excited now, thinking, wow, I could have just given up and not even looked because it was fairly impossible. I didn't think I'd find one, but I looked anyway. So I was feeling very excited. And then, you know what I found? A five-leaf clover. And I just went, man. And I was so excited. And I thought, I'm just going to take this and show it to my girlfriend, and she will know that I'm not a completely useless person. And just as I was about to do that, I thought, oh, hang on. If I pull this out, then if someone else comes looking for a five-leaf clover or a four-leaf clover, they won't find it. And it will have spoiled it for them.
One trick is to get a camera, make the very long exposure type, and then
just photograph it. Yeah, I should have. Yeah, you found a 20-leaf clover.
Oh, you can do that.
Oh, you fake. You're cheating, man. I don't think the leprechauns give you a photo of gold. If you get that 20 leaf.
That's how we know that leprechauns exist, because I photoshopped one.
You photoshopped leprechauns, okay. So anyway, do you see the point? And the point is very tenuous, but I'm getting to this point I'm trying to make. That if I'd pulled this clover out, I would have deprived anyone else. And suddenly I was filled with sadness, thinking, finding this clover is the most exciting thing that's happened to me probably in the whole semester. It wasn't a very interesting degree I was doing. And maybe someone else could have this same amount of fun. So I thought, I'm just going to leave it there. I'm not going to pull it out. And I went back feeling very virtuous. And I was at the bar with my friends and I said, I found a five-leaf clover. And they said, get out of here. And I said, I did. And they said, show me. And I said, I left it there. And they said, where? And I said, here, I'll show you. And I went right over there and I said, there it is, look. And I found the exact spot. And the guy said, wow, that's awesome. I'm showing that to my girlfriend. And he pulled it out. And the reason I told you that story is that's what I would call a spoiler. A spoiler is when you can have an enormous amount of pleasure solving something. And sometimes when you solve it, you really want to tell other people you've solved it so they know how clever you are or wonderful or whatever, you show your girlfriend, whatever. But if you do that, then everyone that hears you say the spoiler doesn't get to have the wondrous fun of finding it out. And I really think with learning and thinking and analysis, that hearing it is nothing compared to doing it. You've got to kick the ball. So my theory is this. In this course, I'm going to give you lots and lots of puzzles. And when you solve them, you should be so proud. But please don't tell anyone else the answer, not because we're trying to have some secret censoring society of people not sharing knowledge or anything. Share knowledge about the course and things like that. Sure, share. Sharing's wonderful. But don't spoil the puzzle for someone else because that's what I think. So that's my please request is please don't do it. Now I think, thinking about it more, this relates something to an educational sort of idea, which is everyone does things for different motivation. There's something called intrinsic motivation, which is you do something to make yourself happy. And there's something called extrinsic motivation, which is you do something to make other people happy. So I'm studying medicine to make mum happy. Extrinsic motivation. I'm studying computing because I love it. Intrinsic motivation. I need to get a high mark because I want to beat my brother when he did this course. Extrinsic motivation. I want to get a high mark because it's a personal challenge I've set myself because I haven't got a high mark ever before in my life. Intrinsic motivation. Now, I think it makes complete sense. It's got fancy long words, but the idea makes complete sense. If you're doing it for yourself, intrinsic. If you're doing it for other people, for glory, for fame, for riches, whatever, to impress other people, extrinsic. Educational research shows one thing really clearly, that if you learn something for intrinsic motivation, you learn it really well and you never forget it and you understand it deeply. And if you learn something for extrinsic motivation, it goes in your head and before anyone can even say the HSC, it falls out the other side. And this has been replicated in so many educational studies that it astonishes me that any educationalists still try and motivate people by extrinsic factors because it will help you pass a test, but then it will be gone. So it won't have helped you. So in this course, I'm hoping you'll become interested in the course and the ideas and you'll want to solve them because they're interesting. And I'm hoping at the other end you'll be learning things because you want to know them, because you want to be a computer programmer, or you want to work for Google, or you want to write video games, or you want to help poor people using the internet in some way, or something like that. So these reasons will make you learn heaps. But if you want to do it to get a high mark, or because you've got to get a high grade to keep your scholarship, or because you're trying to impress someone, or because your parents will be disappointed if you don't get an HD, any of those reasons, they're rubbish reasons. They'll just stress you and they won't lead to good learning outcomes. So extrinsic, external factors, throw them away. Rise above them, be intrinsically motivated. And I remember that by just don't pull out, when you see a four-leaf clover, I reckon just leave it there. Or pull it out and show it to me. Say, look, I was going to pull this out and then, oh, I did. Okay, so clovers lead pretty quickly to trees. Let's just go back to trees and let's look at the difference between depth first searching and breadth first searching on a tree. Oh, and why was I talking about intrinsic versus extrinsic? I think when you post a spoiler, you might be doing it for extrinsic reasons. You might be wanting people to know how smart or clever or amazing you are or something like that. Don't do that. If you're posting it to help other people, that's absolutely wonderful. Please don't post it because I think it'll help them more to not post. But helping other people, and you've posted some great posts to help people, and they've been fantastic, that's a really good thing to do. Oh, you didn't? Is there another Adam in the course?
Probably is.
Where's Adam Black? Where are you? Adam, you've posted some excellent posts. Well done, they're really good. And I'm sure you would post good posts where you post. So please don't post to brag, because bragging's extrinsic, we don't like that. And if you're posting to help, find other ways of helping. My favourite way of helping people is just asking questions. So you don't actually ever give them an answer to a question, you just ask them more questions. Oh, that's interesting, but what about that? Or are you really sure? Or could you give me a proof of that? Is my way of saying, that's wrong. Yeah. But if you do try and produce a proof of it, you'll soon find out why, and that will help. So ask questions rather than give things away is my request. I'm not saying everyone posts spoilers because of extrinsic reasons, but please don't post them for extrinsic reasons. Just solve the brownie point question for your own joy and satisfaction, and you never need to show it to anyone else. Just feel happy in yourself that you solved it. Only show it to the tutor if you want the brownie points. I once had a student who went through the whole course solving all the brownie point questions, never showed anything to his tutor, never got any marks, never did the labs, probably failed the course. Don't know why I'm telling you this. But you know, I was so proud of him. In fact, I once had a student who came to me and said, just before, this was in algorithms, and it was a really intense offering. I was running a very hard algorithms course back in those days. And the student came to me just before the exam and said, I looked at my mark, I think I'm going to fail the course. And I said, why? And he said, well, because for task 1, you set this task, and I thought that was interesting, and it made me think of something else that was even more interesting, and I did that. And then for task 2, I was still interested in the task I was working on for task 1, so I did more of that. And I think he was right. I gave him a little puzzle about how to write a chess program, and he got so carried away that he started investigating algorithms for automatic learning of chess and algorithm optimizations and speed ups. And he was doing and then I taught them about parallel programming. And instead of doing the parallel programming assignment, he started using parallel programming to solve the chess. And then I gave them another assignment on something else, and then he just did more on his chess thing. And I said, oh, that's really awesome. And he said, and I entered my program in the world chess competitions, and like I'm first in Australia and 9th in the world now. and you know, I didn't know anything about algorithms a couple of months ago. And I thought, that is a successful student. It doesn't matter what his transcript says, because that is irrelevant. What matters is that he set out to solve a problem. He learned awesome things to solve the problem because he was intrinsically motivated. He wanted to write a chess program. And now his chess program, in fact, he's bored with chess now. He's writing Go programs. His chess program is one of the best chess programs in the world. He's a very, very clever guy. And I'm sure pretty soon his Go programs will be up there too. In fact, he's doing a PhD in Go programs. In fact, we should get him to come and talk once, except now I've told you, did I tell you anything bad about him? No. So he can come and talk and we can work out who he is. So that's good. I haven't mentioned any of the episodes where he cried in the middle of lecture and the time he wore his pajamas to uni. That was embarrassing. So, okay. So we're now returning to the lecture and we're talking about searching a tree. So we've got a tree that looks like this. We're still stuck on trees. Where is this new data structure that we were promised so long ago? We're just looking at searching on trees for a sec, because there's one more interesting thing to say about searching on a tree. Here's my tree. If I'm going to have to search every node, let's give them all names. A, B, C, D, E, F, G, H, I, J, K, M, N, O. Okay. If I'm doing a breadth-first search, which node am I going to consider first? Let me put that up high so we can see it. And I'll write both the searches out, because I want you to notice something interesting about how breadth-first and depth-first searches go. Notice, like I said before, if we're visiting every node, if there's no way of knowing if we've succeeded in our search till we've visited every node, then it doesn't really matter what order we visit them in. We'll let other criteria affect which order we visit them in. But let's just look at the order that these two different journeys will give us. So breadth-first journey will give us first A. Now what are the children of A? B and J. Right, who comes next? Why is that funny? Okay. You've just got... I'm missing something completely, aren't I? Okay. Okay, so what happens next? We go A, what's next? What's the next node we visit? B. What are the children of B? C and D. Okay, who do I visit next? J. Right, who are the children of J? Okay. Okay. Who do I visit next? C. Who are the children of C? Who do I visit next? D. Who are the children of D? Thank you. Oh. Who do I visit next? Who are the children of I? Who do I visit next? Oh, thank you. Who do I visit next? K. What are the children of K? L, M. Who do I visit next? Ah. My dad taught me this awesome saying once, though I'm going to look a bit silly saying it in this exact context, which was, if a man gets bitten by a dog, have I ever told you this? No. If a man gets bitten by a dog, the dog should be put down. But if the same man gets bitten by the same dog twice, the man should be put down. So, making the mistake once, amusing. Continually making the same mistake, priceless. Okay, so we've got D, I, then we're going to do K. What are the children of K? I'll put them already. Who's next? G. Who are the children of G? No one. Who next? F. Can you notice what happened? As I visited each node, I added the children to the end of the list. And the next node to visit was always the person who was at the front of the list as I slowly pull people off. So I'm adding at one end of the list and I'm pulling them off the other. What structure is this list of children? It's a queue. So if I generate my obligations and stick them in a queue as I go, the queue actually determines completely for me the breadth-first search of the tree. Awesome. I wonder what happens if I do a depth-first search. Oh, I shouldn't have rubbed that out. Okay, let's do another one next to it. But I can work it out again because I know the first one was A and the rest are just this list here. B, J, C, D, I, K, G, F, E, H, O, N, L, M is the breadth-first search of the whole thing. Okay, now that's breadth-first search. Now let's do a depth-first search. Where do I start? A. Who are A's children? B and J. All right, who do I do next? B. Who are B's children? C, D. I'm going to put C, D somewhere. Who do I do next? C. So where probably should I put C, D? In the front. Let's try that. Who do I do after C? Oh, who are C's children? G, F. Who do I visit next? Oh, I've done C, haven't I? Yeah, so C gets taken off. Who do I do next? G. What are G's children? LM, was it? No, G doesn't have any children. All right, who do I do next? Okay, who do I do next? Who are D's children? E, H. Who do I do next? E. Who are E's children? Don't have any. Who do I do next? H. Who are H's children? Don't have any. Who do I do next? J. Who are J's children? I, K. All right, what structure is happening here? What end am I adding at? I'm adding at this end, and what end am I removing from? Same end, it's a stack. So if I, as I visit each node, put its children in a stack, that generates a depth first search. And you've sort of already seen that happen. If you've ever programmed a depth first search recursively to solve Sudoku using a depth first search, all the intermediate obligations are stored in a stack. They're not stored in a stack that we write ourselves. They're stored in the stack the computer uses to nest up function calls. But it's a stack nonetheless, and they're dealt with in stack order. Okay, so when you're looking at the presentation this week, make sure you can see the hidden stack in what's going on. Does everyone understand then the difference between depth first and breadth first search and how to implement them using stacks and queues? Does everyone also understand that it doesn't really matter what order I visit these guys in, if I generate them in this order or this order, if I'm going to have to visit every single one, but it matters enormously if I am doing the sort of search where I can give up. Because then I want to visit them in the order that's going to let me give up as soon as possible. Okay. Are there any questions about depth first search or breadth first search?
Aren't they both like give you the same sort of result at the same sort of time?
If you're going to visit all of the question was, do they give you the same results in the same time? If you're going to have to visit all of the nodes, if that's the sort of search you are, then they're going to give you the same result. And they're going to do it in similar time, and normally, because the computer does function call stacks very nicely, normally the computer might be a bit faster with a breadth first. Oh, and actually function call stacks might be more work than you need. Depending on how you code. Well, well, that's a good chew question for this week. What's a relative advantage and disadvantage of the two? What did you know? The stack is easy to this one's easy to program just using recursion. This one's trickier to program. We've got to set up a queue. What did you notice about the size of the stack and the size of the queue as we were going? The stack stayed fairly small, the queue got fairly big. So this actually turns out to need a lot of extra memory to run. If you track it through, you'll soon see why. Essentially, you've got to keep track of all the uncharged obligations that you've generated already. Whereas with a depth first search, your objective is you're going down whenever possible. Going down is knocking someone off the stack as quickly as possible. So you're trying to discharge your obligations as quickly as possible and incur new ones at a slower possible rate. With a breadth first search, you're trying to incur new obligations as fast as you possibly can, and you discharge them very slowly. So in terms of the amount of memory you need to store your obligations, breadth first can be less efficient that way. But yeah, if you have to go to the end, then they're both, you have to consider considerations like memory. But if you don't have to go to the end and you can give up early, then they make the world of difference. Because some problems, you can give up early on this one, and some problems you can give up early on this one. And you'll just have to look at the problem and get a feel for it and work out which search is going to be most likely to give you what you want as quickly as possible. Yeah, they've got the same worst case time complexity. Yeah. So, but if we think about average case time complexity, yeah. Oh no, not at all. If you have any information that will let you work out that one of them is more likely to find the destination earlier than the other, normally the difference that makes is astronomical. So it depends on the problem you're trying to solve, but for a large class of problems, one or the other of them is massively chews up the other one. So make sure you always think of them both and work out which one's going to find the one I'm looking for as quickly as possible. In the next course you do, 2911, we will spend forever doing tree searches. Not forever, it'll be heaps of fun. But I made it sound really boring. But the way I run 2911, because I'll be taking you for 2911 next year, we're together for 2 semesters, I think, which is very rare, which is very exciting for me, because I get to know you all that much better. And if you really hate my style of lecturing, time to bail now, because there's another whole semester to go. In 2911, how I do it normally is I give you large problems. Each week there's a problem, and you just work through the problems. And we'll be looking, and it's a course where you come up with solutions to problems. So you will be, at the end of that course, a fine problem solver. So if we went to the old PAPP, problems, algorithms, programs, procedures, processes, thank you very much. In that course, 2911, we're very interested in this step here. How do you go from a problem and pick the right algorithm, or design or build your own algorithm? In this course, we're really just analysing algorithms and analysing problems, and occasionally we do this step. The next course is all about this step. It's a beautiful course. Okay, all right, now we're running a bit tight on time. I did want to, I'll just go for I'll do one more point and then I might run this lecture into the next lecture a little bit too, since they're back to back. Now I'm trying to work out which is the best thing to do. We've got two choices. It's not that hard, Richard. Come on, make a decision. All right, it's this. I will actually just show you a clip, I think, and then we'll have the break. Now, someone wanted to show you another movie during the break, so there's someone that wants to show you an ad. So after I've shown you this clip, there'll be a brief pause. You can get up during my clip or after my clip. Then there'll be a brief ad. Then the lecture will resume. Here's a clip I wanted to show you, and I just wanted to tell you one thing before I can show you the clip, and that is this. In this course, and in the previous course and in the next course, we spend a lot of time talking about the importance of writing beautiful programs and writing correct programs and writing well-documented programs. And I noticed that a lot of people, every year I notice this, and I've noticed this for 20 years, if you come in, and I noticed it with me when I was a student, if you come into a computing course already knowing how to program, you're very resistant to these ideas. I was very resistant to these ideas. And when someone says write a nice, neat program, you go, no, why bother? I can write a clever, fast one now. Why do I have to write it your silly, long, roundabout way? It's just annoying and boring. I can write it my really clever way. Sure, it's less clear, but I know exactly what I'm doing, and that's all that counts. And doing it your way is just unsatisfying and unfun for me. And I was very hostile to the notion of style until one day I suddenly got it when I had a program that I'd written a couple of months before, and it was for a video store or a video rental store. In those days, there were libraries, they were called. And they really were videos. And I'd written some software and it needed to be changed. And I'd written it in BASIC. And the guy from the shop said, oh, there's a problem, you need to change something. And I looked at it and I couldn't work out what the hell I'd done because I'd written it like a year ago or something like that. And I suddenly thought, oh no, why am I spending all my time debugging and fixing and trying to work out what's going on? I'm not getting any time to do the fun stuff and use my brain and solve the clever problems and pick the good algorithms and do all that stuff. Spending all my time getting my hands dirty with the boring, annoying, irritating stuff that things keep going wrong. And I thought, there's got to be a better way. And I had a beautiful tutor at uni, this most wonderful woman, who taught me, beat into me really, with a big hammer, the importance of writing beautiful code. And as I started writing more and more beautiful code, all my problems started falling away. And it just was very fulfilling and satisfying. And I started to enjoy computing again. Instead of it being a horrible hacky thing, it became this very beautiful experience. And what she said to me is, if you write it in a complicated way, in addition to all the other unpleasant side effects of it, the company is really dependent on having you there. For example, I worked in an insurance company and the valuation system was written in APL. APL is a horrible programming language. It actually stands for A Programming Language, APL. It should be called AHPL. Has anyone ever programmed in APL? Simultaneously exciting and horrendous. Each function it's like a hacker's dream. Actuaries use it, so they're the ultimate hackers. Amazingly smart with no common sense whatsoever. So each function has just one letter. There's nothing that has more than one letter. There's no notion of a comment. Functions act on other functions. So chaining three functions next to each other gives you this super complex nested meta function that does higher order things. Four characters of APL can be incomprehensible. You can be standing there all day just trying to work out what those four characters put together do because everyone is cross-modifying each other in crazy ways. An APL program is never longer than a page, even if it's doing the world's most complex task, entirely revaluing an entire life office, working out the payroll for everyone, generating a mailing list, posting it to everyone, collecting the responses, noticing spelling mistakes in playing a game of tic-tac-toe. Easy. It's a page of APL. But it's a page that you could stare at for 3 weeks and not understand. And my first job in the insurance company was actually, the guy said, oh, we've just changed our interest rates. Can you update this APL program? And he gave me this tiny bit of code and I was on it for more than a week before I even dared touch it. I was just staring at it going, what? And that does what? And this line modifies every one of the previous lines. And there's so many functions in it that instead of giving them longer, like if you have more than 26 functions and you just have single letter function names, you would think, what are you going to do? Have double letter variable names or function names? No, no. APL says use uppercase. So you go, okay, now I've got 52 function names. But APL has more than 52 functions built in. So they extend the keyboard. There's extra modifier keys and you've got to buy a special keyboard. And they use Greek letters, Hebrew letters, Latin letters, every letter under the sun. So you're just constantly, and you need to have a special keyboard to even program this thing. And every character is just one letter long. It's the most horrible language in the world. And I was just having this complete fit. And eventually I said, I'll just throw this out the window and write it completely from scratch myself. And my boss said, yeah, that's what we always do. We never actually correct a program if it's broken. We just throw it out and write a new one. And I said, well, what about the valuation program? And he said, oh man, Bill, or whatever his name is, Bill Smith is the smartest guy in the world. He was the old chief actuary. He wrote the whole valuation system himself. He was a complete genius. He wrote it all in APL. It's like 10 pages of APL. What? You can't have that much APL. The world will explode. And he said, whenever the company does a valuation, which it has to by law every year, we have to get Bill Smith in from retirement and pay him a ridiculous consultant fee because no one else can run the code. And we live in fear of one day him being hit by a bus. And this is, amusingly, this same thing my awesome computer tutor told me. She said, when you write your code, even if it works fine for you and you think it's okay to write messy, crappy, ill-thought-out code, your company's in trouble because one day you're going to be hit by a bus and someone else is going to have to understand it. So I sort of coined this motto after that the adversary drives a bus. The adversary is always out to get you. He's a bus driver. So that's the last sort of teaching point I wanted to make. Now, I have what do I want to show you? Let me show you. I have something here about kicking the ball. This is about surviving and not giving up. Let's just turn the lights off for a second. Jump to the laptop. Put down the screen. Never ever, never ever give up. Here it comes. You might already know this. Can everyone be quiet? Okay, all right, let's take our break then.